Okay, good. Hi everyone, my name is Carlos. I'm studying I will presentation my work is a temperature dependence magnetization spin flip transition in Antulio iron garnet films and in particular in isotropy. Why is our error important for the study? This material extending study in a book form, and it's oxide and a magnetic insulator too. The formula unit there is at Earth. You can be put the thulium, gadolinium, yttrium. The similar materials are presented the last presentation. It's a Ferri insulator with multiple magnetic sublattice. You see here the structure. You have a three magnetic structure where the iron 3 plus tetradiagonal sites and in the oxide, and the iron 3 plus and the octahedral sites is have a super exchange interaction between them, and then weak coupling with thulium. With this material, it's a ferromagnetic coupling, which one iron and antiferromagnetic coupling another iron. It combining these three magnetics sublattice, you create a rich magnetic phenomenon. And when you change this head earth, it's possible to tune in some properties, interesting properties in the films. But after you talk about the films, we talk the magnetic behavior in the book systems, very important. Here you see the magnetic moment with temperature with different air earth. You can see the terbium, dysprosium, gadolinium have a high magnetic moment associated in these atoms. So it's possible to observation one phenomenon very important is the compensation temperature in these materials. This magnetic net is equal to 0 in these regions here. It's depend the atoms when you introduce these materials. When you have thulium, for example, we have a small magnetic moment associated him, and you not observe this compensation because we don't win the interaction with the other sites, iron sites. But when you go to the confinement systems in the films, its material is very interesting because it has some applications, especially in spintronic magnetic magnonics, because he present the magnetic dumping, a small magnetic dumping material. You can create some tuning based on wind strain and substrate in these films. For example, in the measured smoke with different annealing preparation of these materials, it's possible to change the compression for attention when you apply at 900 Celsius degree in these materials. You observe, in this case, perpendicular magnetic isotropy. So these materials have not only for application a free spin waves, but the application for a memory switch resistive devices, for example. So the objective of my study is investigating magnetic behavior in fundamental aspect and then strain thulium iron iron garnets in the films with thickness and 13 nanometers. And we explore emergence and the compensation like temperature. We observe in the compensation like temperature close to a 50 Kelvin. It's not observed in bulk, so it's very interesting phenomenon to understand. When demonstrated to field-induced spin flip transition into sublattice, we analyze an element-specific contribution iron in thulium using X-ray magnetic circular dichroism. So it's technique possibility to understand the effect of the coupling in the anisotropy sublattice level. So first of all, I will show you magnetic behavior, okay? And then the thulium iron garnet, its substrate GGG have a large paramagnetic signal. So this because of that, you have some noise about these curves. And we observe what is expected in the MOX measurement. We have a large PMA with 900 annealing, 900 Celsius degree with annealing preparation. And you see the systems to increase the coercivity when you decrease the temperature. Have some signature when you talk about the compensation systems. Respected, the coercivity increase exponential when you decrease the temperature. And in specific temperature, you have some diversion of the coercivity. You observe close to a 50 Kelvin in these systems. So it's some signature, the compensation, but we use in this representation a compensation like temperature because it's like temperature, because the compensation like, because when you see an X-ray magnetic circular dichroism, you have some signature in this temperature point, temperature compensation point, because the sublattice and magnetic sublattice change this orientation when you cross this temperature compensation. So what is X-ray magnetic circular dichroism? You excited the electrons of the material using synchronous light with the chirality positive and negative. When you have some aspect with the light chirality, your interaction with the material, you have the shed light about the magnetic behavior in this material. So when excite the light, when a core level electrons excite to the energy band, these electrons, and you study in the specific edge of energy in this material, you see two, in this case, two spectra, X-ray absorption spectroscopy with different chirality, and you have one minus other, you get the X-ray CD spectra. And you see in the L23 item, you see the antiferromagnetic coupling expected in this between this item, and no inversion. It's important. You have not observed inversion, no compensation with iron. So you don't have this information about the change of the orientation. The thulium, you observe the decreasing, but before the 50 Kelvin, you decrease again the dichroism. When you apply the magnetic field systems, and you apply 1, 5, 7, and 9 Tesla, and you observe no change in the spectrum of iron because you have a very strong magnetic couple between them, but you have a weak coupling with iron with Earth, so it's possible to see the different dichroism. When you increase the temperature, you change the signal of the dichroism. And we elucidated the change, the orientation of thulium, because you see the projection in Z direction. You see this projection in this spectra. So it's possible to understand the quantitative magnetic moment of total magnetic moment of the atoms. And it's possible to understand to the spin and orbital magnetic in this material. So you see here in a room temperature, the magnetic moment of spin, the iron net, the material, and the magnetic moment of spin, the thulium. The thulium has a small magnetic moment at room temperature, but you expect in Earth change and increase the magnetic moment in the low temperature. you observe this material. You observe exactly this in 20 Kelvin. You see the change the signal only the Thulian, because the Thulian have the spin flip behavior. Okay, you see a great information about the importance of the magnetic orbital in the Thulium when you decrease the temperature, because it has a high spin orbital coupling in this material. I think it's essential to understand why appear the compensation like temperature, the compensation like phenomena in these materials. We believe we have some hypothesis, and I try to elucidate it in the next year with neutron diffraction, or the change the systems with a collinear to a non-collinear configuration, non-collinear magnetic configuration, these materials. We see, we are expecting the free atoms in the systems with the Thulium increase the magnetic moment totally with you decrease the temperature. But this information is about the projection direction Z of these atoms. You observe the change of this projection close to the temperature compensation, the minimum magnetization of the material. In the iron, you observe the same behavior. You reduce this projection. So you see, because of the change in the direction, it's possible to create a non-collinear systems, and you believe you have some content. It's because of that the change the structure, magnetic structure, you believe created the compensation phenomenon. So you identify the compensation like temperature. You observe XMCG, you observe the analysis, the contribution dominated at Thulian low temperature, and reveal 3 distinct magnetic regime in temperature. And I finish, and now I'm ready for the answers.
Okay, thank you very much for this nice talk. If anybody has questions, please write them in the chat, of course, or raise your hand and we'll ask you to unmute. So I have one quick question. Maybe I'll jump it off here. You quantified the orbital to spin ratios with XMCD, I assume by taking the integral of your XAS difference. Looking at your L3 and L2 profiles, I'm just wondering how accurate these orbital to spin contribution or ratios are, because I know when you do XMCD, these integrals can get quite they're quite sensitive to any noise in the system, and some of these profiles you show have a lot of noise. It appears in the pre and post stage. So how do you deal with that?
The experiment, we use a total electron yield to capture the information. I think it's have no much noise in the measurement. Okay, we see have a good. Okay, for example, here you have a good information about the dichroism. It's possible to introduce some rules, and they quantify the magnetic moment, both for orbital and the total, or orbital and the spin characterization. It's possible, and I think it's a great characterization about the relation between the orbital and the spin. The information we look for, it's very common to find the same characteristics in these materials. I don't know the response to your answer correctly.
Yeah, no, sorry. I was just, I guess, very curious about the analysis to get the orbital to spin ratio.
The analysis is it's not easy. So
yes.
you have some integrals for this calculation. It's necessary to have some quality in your spectra. For example, this line, it's very don't have linear linear behavior. So it's very important to have a between these spectrals. So
Thank you very much.